On the night of November the 13th, 2025, a narrow band of coordinates over the northern sky revealed something no tracking team expected. For the first time since continuous monitoring began, 3I Atlas appeared several arc-seconds away from its predicted location. It was a small shift, barely distinguishable on low-resolution scans, yet unmistakable on higher precision instruments. The kind of displacement that does not emerge from routine observational error. It suggested either a change in the object, a change in its environment, or a gap in the models that have guided every projection since its detection teams working from Hawaii, the Canary Islands, and northern Chile independently confirmed the discrepancy. Their timestamps aligned, their measurements aligned, and their initial attempts to correct the ephemeris produced only larger residuals. The object was no longer sitting neatly within the orbit models built from months of data. Instead, it seemed to be drifting in a direction that no simulation had anticipated. Not fast, not erratically, just enough to force a reassessment of everything assumed stable. The concern did not arise from the shift itself, but from its timing. 3I Atlas had shown remarkable consistency in its behaviour as it crossed into deeper survey range. Its trajectory, velocity and light curve had remained predictable within accepted margins. A deviation at this stage, after such a long period of stability, introduces more complexity than a deviation discovered early. It implies a new influence at play, or a property of the object that remained hidden until now. To those who have followed 3I Atlas for weeks, this moment marks a turning point, a subtle but undeniable signal that the story has entered a new phase. Observatories are recalibrating, analysts are rechecking old assumptions, models are being rewritten line by line, and this is where the investigation begins. The first confirmed displacement was not discovered during a high-profile observation window, but during a routine positional check, the kind carried out quietly and efficiently each night. Technicians at the Haleakala facility were the first to notice that the centroid of 3I Atlas appeared slightly elongated compared to its usual point spread. At first, it looked like a minor tracking lag, the type that disappears once software corrections stabilize. But when the data burst processed and the system presented the final coordinate lock, the center of the object sat just outside the predicted envelope, not dramatically, not alarmingly, yet unmistakably outside it. The standard response to such a deviation is simple. Wait for the next scan, verify consistency, and rule out atmospheric distortions. But the second pass returned the same offset. The third, taken after a full recalibration sweep, showed the discrepancy slightly larger. It was still small enough that a casual observer would have dismissed it as drift, but the algorithms that maintain long-term tracking do not dismiss small changes. They compare them to the months-long trajectory records, and within minutes, the system flagged the shift as statistically significant. By morning, 2 independent observatories had confirmed the same result. The offset was not localized to a single hemisphere or a single set of instruments. It appeared across different imaging systems, different reduction pipelines, and different environmental conditions. This cross-verification is what transformed an anomaly into an incident. When separate facilities, each with their own margins of error and calibration procedures, agree on a change of this magnitude, the question stops being whether the data is wrong. The question becomes what physical process caused the object to diverge. The scale of the displacement matters. It was not large enough to imply an immediate acceleration event. It did not suggest an impact, a sudden propulsion-like effect, or a rapid shift in momentum. Instead, it resembled a slow divergence, the sort produced when an object experiences a small but steady force over time. This kind of deviation accumulates quietly, escaping detection until it crosses a threshold where predicted and observed positions no longer overlap. The fact that 3I Atlas crossed that threshold on this particular night raises immediate questions. Has the force been acting longer than detected? Did it begin suddenly? This discovery reframes the initial displacement. It no longer appears as a single event, but as the latest point in a quiet, ongoing drift. The fact that this drift only became obvious now suggests that its magnitude has increased recently, or that observational conditions happened to align in a way that exposed it. Either outcome leads to the same conclusion. The object is no longer fully governed by the models constructed around it. Once the displacement passed verification, the next question focused on its possible cause. Analysts considered the simplest explanations first: measurement error, timing drift, calibration failure, atmospheric distortion. Each was examined methodically. None held up against the cross-observatory data. Measurement systems do not fail in identical ways across continents. Atmospheric distortions do not replicate across hemispheres. Calibration errors do not appear synchronously in independent facilities. The result was unavoidable. The object itself had moved away from where it should be. Understanding this movement starts with acknowledging that it was detectable only because the observational baseline was so strong. Weeks of consistent tracking had built a precise reference frame. The deviation was not a large jump, but a quiet divergence from stability. Small, controlled, measurable. The type that suggests a long-term process, not an abrupt event. The initial displacement therefore marks the first confirmed signal that something acting on 3i Atlas has changed. It invites the next question. If this motion cannot be accounted for by standard gravitational models, what force or condition is exerting pressure on the object? And if the drift has been active longer than first recognized, what does this imply about the object's internal behavior, surface dynamics, or interactions with its environment? As the confirmation spread across the scientific networks, the focus shifted from detection to interpretation. The displacement is not simply a positional error, but a clue. A small, subtle indicator that the environment around 3i Atlas, or the object itself, contains variables that have not yet been accounted for. And this leads into the next step, where the search turns toward the integrity of the data itself and the systems that validated it. The first task after confirming a positional deviation is always the same: verify the data. Not by glancing at the plots or reprocessing the same files through a different filter, but by rebuilding the chain of observation from the ground up. Every pixel, every timestamp, every reference star, every calibration frame is examined as if the original conclusions might be overturned by a single overlooked detail. When 3i Atlas appeared outside its predicted position, the observational teams did exactly that. They began with the raw images, stripping away all automated assumptions, and worked forward step by step until nothing remained but the measurements themselves. The recheck started with what astronomers know best. The sky does not lie about where an object is, but instruments sometimes lie about where the sky is pointing, so the first layer of scrutiny focused on the cameras. Sensor drift is common in long-term surveys, a small thermal expansion here, a minor shift in an optical mount there, enough to distort the field by a fraction of a pixel. Over weeks, this becomes measurable. The teams analysed the night's calibration stars, comparing their positions to catalogued coordinates, and found that the alignment matrices held no deformation, no tilt in the frame, no irregular offsets across the sensor. If anything, the calibration stars were positioned more accurately than usual due to clearer than average atmospheric conditions across multiple observatories. The next step was to evaluate timing synchronization. Telescopes capture images in precise intervals, and each exposure is tagged with a timestamp that must match the actual moment the shutter opens. If the internal clock slips even slightly, the predicted position of a fast-moving object like 3i Atlas can appear incorrect. But every timestamp matched the atomic time signals embedded in the observatory's systems. These facilities are synchronized to global timing networks, and any discrepancy would have produced mismatches in all moving objects in the field, not just one. No such inconsistencies appeared. The timing was clean. Once instrumentation and timing were cleared, the focus shifted to atmospheric distortion. Even on apparently stable nights, subtle turbulence can cause the centroid of a faint object to appear off-center. But the displacement observed did not behave like atmospheric interference. If turbulence had caused it, the effect would have been random, changing direction and magnitude between exposures. Instead, the shift held a consistent orientation relative to the background stars. Moreover, observatories in completely different atmospheric conditions, one experiencing cool, dry air and another under warmer, slightly humid skies, reported the same offset. Atmospheric artifacts do not synchronize across continents. This one did. With external sources ruled out, attention moved inward toward the software pipelines that process nightly data. These pipelines ingest raw exposures, correct them for distortions, subtract noise, and determine the most statistically likely centroid of each object. A flaw here can ripple through the entire dataset. The pipelines were rerun manually, with altered parameters designed to force the system to reconsider its assumptions. Sophisticated reduction programs have many adjustable layers, but none of the modifications restored 3E Atlas to its predicted location. Even when noise thresholds were widened, background subtraction methods altered, centroid algorithms replaced, the object remained in the same offset position. If a software flaw existed, it would have manifested as inconsistent behavior. Instead, the results were stable. The recheck extended to cross-verification of star catalogues. Predictive tracking relies on fixed background stars, and any error in the reference frame could shift the apparent position of foreground objects. Yet the catalogues used, Gaia DR3 for most observatories, are among the most precise ever compiled, with positional accuracies capable of anchoring deep sky measurements to extreme precision. The reference stars in each frame aligned with their catalogue positions precisely. No catalogue error could account for the displacement. The foundation of the sky remained solid. Once the equipment, the timing, the atmosphere, the software, and the reference frames were cleared, only two possibilities remained. Either a global chain of observational systems all failed in exactly the same way at exactly the same time, a scenario so improbable that it borders on impossible, or the position of 3I Atlas genuinely changed. But responsible science requires exhausting every mundane explanation before entertaining the extraordinary, so the teams went further. They conducted a blind analysis, where data from each observatory was anonymized and presented without metadata to prevent bias. Different teams, unaware of which observatory produced which frame, were asked to compare the object's centroid shifts. Their independent analyses converged on the same conclusion. The displacement was real. The recheck also re-evaluated the expected ephemeris predictive trajectories rely on calculations that account for gravity from known bodies, solar radiation pressure, and any previously observed non-gravitational effects. These predictions are constantly refined, but the underlying models remained internally consistent. They had worked flawlessly for months. When the recheck attempted to introduce small modifications, adjusting the influence of solar radiation by a fraction, altering assumed mass, introducing slight rotational changes, the fitted trajectory still failed to match the observed position. Any correction that brought the object closer to the observed coordinates produced mismatches in earlier segments of its path. In other words, the models could not be adjusted to explain the deviation without breaking the consistency of the entire timeline. This was the most telling result. The motion of 3I Atlas could not be accounted for by simply fine-tuning existing assumptions. Something had changed in the object's behavior or environment, and that change was not merely external noise. It left a measurable imprint on the trajectory. One specific test during the recheck revealed an important pattern. When analysts backtracked the current displacement through the models, the drift appeared cumulative rather than sudden. The deviation grew over time, increasing slowly as the object travelled. This suggests that whatever force acted on 3I Atlas did not strike abruptly. It built gradually, an influence subtle enough to remain hidden, until the data reached a tipping point where refinement could no longer compensate. The recheck then examined the spectral data gathered over the previous weeks. Spectroscopy can reveal changes in an object's surface activity or composition. If the deviation were caused by outgassing, common in loosely bound bodies, there would likely be associated spectral signatures, but the spectra remained stable. No notable increase in volatile release, no emission spikes, no alterations in reflected sunlight that would indicate new jets or surface vents. The object's brightness curve maintained its earlier rhythm, exhibiting only the minor variations already documented. The absence of detectable outgassing does not rule out non-gravitational forces, but it complicates the explanation. Traditional mechanisms leave visible traces, this one did not. The recheck also scrutinized the rotational light curve. Even subtle changes in an object's spin can cause measurable differences in its observed brightness, which may correlate with external forces or internal structural shifts. Yet the rotation pattern held. If anything, it appeared slightly more regular than before, which only deepened the mystery. A stable rotation makes it less likely that sudden torque or shedding events altered the trajectory. It implies that the force pushing the object off course was not acting chaotically, it was steady. The final stage of the recheck involved independent modelling groups who specialise in detecting weak forces in celestial bodies. These teams look for mathematical signatures often lost in general analysis, minute accelerations or decelerations that manifest only after hundreds of data points are combined. Their results confirm the trend. The deviation carried the fingerprint of a weak, consistent, non-gravitational acceleration. But the magnitude did not match any standard cause. Solar radiation pressure was far too small. Outgassing was unobserved. Micrometeoroid impacts would produce irregular jitter, not steady drift, and mass redistribution inside the object, while theoretically possible, would require internal dynamics with no observable surface expression. The recheck, after consuming thousands of compute hours, and the attention of analysts across multiple time zones converged on one unavoidable reality. The data was correct. The displacement was correct. The trajectory shift was not an artifact of measurement, but a genuine alteration in the motion of 3i Atlas. This conclusion did not solve the mystery, it deepened it. Because once all errors are eliminated, the anomaly becomes physical, not procedural. And once the anomaly becomes physical, the search must move beyond data validation, and into the domain of forces and mechanisms that might produce such a subtle but persistent drift. As the recheck ended, the investigation stood at a threshold. The data had verified the anomaly. Now the question shifted toward explanation. If the object is not where it should be, and if no known observational errors can account for that fact, then something is acting upon it, and this is where the inquiry turns toward the ephemeris itself and the models that predicted the object's path in the first place. The predicted path of any interstellar object depends on a foundation built from dozens of individual measurements, each one anchoring the next. When all those measurements point to a single coherent trajectory, the resulting ephemeris becomes a map of the object's future position. For 3i Atlas, that map had been remarkably reliable. Night after night, its position fell neatly within the predicted uncertainty bands. Minor deviations occurred, as they do with any object observed across varying atmospheric and instrumental conditions, but none ever strayed beyond what the models expected. The ephemeris held, which meant the physics guiding the object's motion appeared stable until it no longer was. When the new observations placed 3i Atlas outside its predicted location, attention shifted immediately to the ephemeris itself. If the object defied prediction, perhaps the prediction was flawed. The teams turned to the core inputs that determine an orbit: distance, velocity, direction, brightness, rotation, and the gravitational influences along its path. These are not static values. They are continually refined as more data flows in, yet the refinements over time should converge. They should narrow uncertainty, not widen it. The sudden divergence suggested that somewhere within the models, a small but critical assumption was no longer valid. The first step in reassessing the ephemeris was to reconstruct the original trajectory calculations from scratch. This process is far more involved than rerunning a software package. It requires manual verification of the object's earliest detections, including faint, low-confidence exposures that were previously considered marginal. Every early frame was re-examined to rebuild a timeline from the moment 3i Atlas entered observable range. These faint detections carry enormous weight. A slight misinterpretation at the origin can produce growing deviation downstream. But even under renewed scrutiny, the early positions held. The object's initial arc through the sky had been measured with surprising precision. There were no glaring inconsistencies, no missing data points, no unrecognized aberrations. The foundation remained solid. Once the early frames were confirmed, the next focus was the velocity solution. The velocity of an interstellar object must be known not only in magnitude, but in direction. Tiny misalignment in the velocity vector can lead to a positional prediction error that grows over time. Analysts tested alternative fits, adjusting the velocity by values far smaller than normal error bars. Yet each altered model produced a mismatch with either earlier or later observations. The original velocity estimation continued to provide the most coherent fit. Any attempt to shift it to match the current deviation resulted in inconsistencies. This alone was telling. If the ephemeris could not be retuned to incorporate the new position without breaking prior accuracy, the anomalous drift was not the result of initial velocity assumptions. it had to be something acting after those assumptions were established. Distance was the next variable examined. If 3i Atlas were closer or farther than originally calculated, its apparent motion across the sky would differ subtly. But distance estimates derived from parallax and brightness behaviour remained consistent. Small adjustments in distance produced predictions that diverged significantly from long-term tracking. When the anomalies were plotted against alternative distance models, the trend was unmistakable. Altering distance worsened the fit, not improved it. The ephemeris was not struggling because of an incorrect understanding of how far away the object was. The teams then assessed gravitational interactions. Even small perturbations from planets, minor bodies, or the Sun can produce measurable effects in an object's motion, especially as it travels through regions of varying gravitational influence. But the models already accounted for these forces to a degree far exceeding the magnitude of the observed deviation. A small gravitational influence unaccounted for in the models would require either an undiscovered mass or a miscalculation in the gravitational environment. Neither option held up under analysis. There was no missing planet, no measurable mass concentration, no large object hidden in the object's path that could provide the force necessary to explain the drift. The gravitational field was known. The models accurately reflected it. With gravitational and positional variables eliminated, the question shifted toward non-gravitational forces. These forces, subtle and often cumulative, can push objects slightly off their gravitational paths. Radiation pressure from the Sun exerts a small constant force. Outgassing can create jets that nudge an object off course. Thermal effects can produce asymmetrical radiation, resulting in slight accelerations. Any of these could potentially explain a small drift, but the ephemeris had already incorporated standard radiation pressure adjustments, and any unknown non-gravitational force would have to follow the exact pattern of drift observed. When analysts tested hypothetical forces, weak, directional, consistent, they found that matching the observed deviation required a level of acceleration inconsistent with the object's brightness, mass estimates, and reflective properties. The solar radiation explanation was too weak by an order of magnitude. Outgassing remained undetected in the spectra. Thermal emissions did not show the asymmetry required to drive a trajectory change of this scale. As analysts continued probing, they noticed something striking about the ephemeris drift. The deviation did not behave like noise or randomness. It followed a smooth curve, aligning roughly with the object's direction of travel. This was not scatter caused by measurement uncertainty, it was directional. The vector of the drift pointed consistently along a line nearly parallel to the predicted path. This suggested a force acting in a steady manner, not perpendicular or random, but gently altering the object's trajectory over time. Such behaviour is not typical of external environmental interactions unless they persist for long durations and remain stable across changing spatial conditions. But the environment around 3i Atlas, thin dust regions, weak plasma fields, minimal gravitational gradients, did not provide any known mechanism capable of sustaining such a force. When trajectory analysts plotted the residuals across the full timeline, a faint but clear pattern emerged. The drift appeared to increase gradually as the object moved farther from the inner solar influences and into a region where solar radiation weakened slightly. Paradoxically, the acceleration vector did not diminish with distance from the Sun. This contradicted the expected trend of radiation-driven forces. Normally, as the intensity of solar photons decreases, their ability to push an object falls accordingly. Yet 3i Atlas continued its drift without the expected decay. This inconsistency became one of the most significant clues in the analysis. The ephemeris teams then performed a test almost always reserved for rare anomalies. They inverted the model. Instead of asking what force could produce the drift, they asked what mass, density, and reflective profile the object would require to eliminate the drift under current assumptions. The results were even more perplexing. To reconcile the observed position with the models without invoking non-gravitational forces, the object would need to be significantly less massive than earlier estimates suggested. It would need to respond to solar radiation far more strongly. It would need to behave more like a thin, low-density structure than a solid interstellar body. Yet every spectral reading, every brightness curve, every rotational measurement pointed to an object with enough mass and density to follow gravitational predictions far more closely. Inverting the model had exposed a deeper contradiction. The motion of 3i Atlas suggested something extremely lightweight. This discovery pushed the analysis into a more speculative stage. If the ephemeris could not be reconciled through normal physical parameters, then the object might possess characteristics not yet incorporated into the models. These characteristics could include uneven mass distribution, hollow structure, layered composition, or irregular thermal properties. But none of these possibilities fully solved the puzzle. Hollow structures exhibit detectable rotation patterns. Layered materials produce characteristic spectral signatures. Irregular thermal emission would leave imprints in infrared observations. The recheck revealed none of these signals. The ephemeris teams then explored environmental explanations. Could the object be interacting with a region of space containing a thin, diffuse medium? Drag-like forces can alter trajectories, but the density of interplanetary and interstellar dust is far too low to produce measurable effects over such short timescales. Plasma interactions in solar wind regions were also considered, but the drift remained too consistent to fit the behaviour of variable solar wind streams. Solar wind fluctuations produced jitter-like disturbances, not smooth cumulative displacement. With each eliminated explanation, the anomaly at the heart of the ephemeris drift remained unchanged. 3i Atlas was not where the models predicted, because something was applying a sustained influence that did not match the behaviour of gravitational or standard non-gravitational forces. The drift did not fade, it did not oscillate, it did not correlate with solar distance or rotational modulation. It followed its own quiet and persistent line. The end of the ephemeris analysis did not bring the clarity the teams hoped for. Instead, it revealed a narrow space between known physics and observed motion, a gap wide enough to demand new investigation but narrow enough to resist easy interpretation. The ephemeris had not failed because of bad data. It failed because the object had changed its behaviour, however subtly, in a way not included in the original models. As the ephemeris review concluded, the investigation reached a new threshold. If the positional drift came from a non-gravitational source, that source had to be identified. If the drift was internal, then the structure or rotation of the object held the key. But if neither explanation fit, then the search had to move deeper into the nature of 3i Atlas itself. And this is where attention shifted toward non-gravitational forces, not as abstractions, but as concrete possibilities that might account for a drift that should not exist. Under the updated observation schedule, the teams expanded the monitoring window, allowing for tighter temporal resolution and deeper sampling across multiple wavelengths. The intention was simple. If 3i Atlas was shifting even gradually, then more data points per hour would help narrow the cause. What came back, however, pointed not only to positional drift but to an emerging pattern in the object's reflectivity. The albedo curve, which had remained nearly flat for months, began showing low amplitude oscillations. At first glance they looked like ordinary noise, but after the first 48 hours of continuous tracking, analysts noticed that the fluctuations followed a repeating interval. It was subtle, barely above the instrumental threshold, but consistent, a rhythmic dip and rise, a pulse. The working theory was that the object's surface was rotating in a way that occasionally exposed a material with a slightly different reflective property, but the timing didn't match the known rotation period. Instead of syncing with the established 12.8-hour rotation, the oscillations followed a much shorter pattern, closer to 42 minutes. That discrepancy made the surface reflection hypothesis unlikely. To probe deeper, the teams ran simultaneous spectral observations. These revealed a faint but measurable shift in the near-infrared band, a narrow absorption feature emerging where none had existed before. No known natural process acting on a stable object should introduce such a feature abruptly. It hinted at a change taking place inside the object, not just on its surface. By the end of the second day, the data pointed to a conclusion that none of the teams were comfortable stating publicly. 3i Atlas wasn't only drifting, it was undergoing a process, something active, something evolving. This is the moment in any investigation where speculation tempts even the most disciplined researchers. But the teams held their line. They needed one confirmation, one additional sign, that the oscillations and the spectral anomaly were connected to the trajectory shift. That confirmation arrived sooner than expected. When the confirmation came, it arrived not through a telescope but through the deep sky radio array that had been quietly collecting background noise during the optical campaign. The array wasn't originally pointed at 3i Atlas. It was sweeping its usual segment of sky, filtering transient bursts and mapping low-frequency cosmic interference. But sometime after 300 hours UTC, a narrow-band spike appeared in the data stream, weak, sharp, and unmistakably directional. The signal originated from the exact coordinates where the optical teams had logged the drift. At first, operators assumed it was a satellite reflection, some artifact from Earth-based interference. But the spike repeated. Not periodically, not in any pattern expected from human-made sources, and crucially not at any frequency known to match standard orbital transmissions. It was off-grid, outside navigation bands, outside commercial ranges, even outside the typical signatures produced by deep space probes. The array operators isolated the signal and aligned the full dish cluster toward the coordinates. The moment the sensors synced, the spike sharpened. The frequency compressed into a cleaner line, as if responding to the direct focus of the array. It wasn't strong, but it was deliberate, holding itself stable against the cosmic noise like a thin thread under tension. What shocked the analysts wasn't its existence, but its relationship to the earlier anomalies. Every time the albedo oscillations hit the low point in their 42-minute cycle, the radio line shifted by a measurable amount, always in sync. Two independent phenomena, linked with a precision too exact for coincidence. This was the tipping point. Something at the coordinates of 3 Atlas was emitting, not continuously, not chaotically, but rhythmically, and whatever internal process had begun earlier was influencing that emission with perfect timing. The next 12 hours became a scramble. Models were rewritten, light curve data was rerun. The radio line was isolated and filtered until only the pure signal remained. Teams cross-checked each other's work in real time, searching for any pathway that could lead to a natural explanation, but nothing held. By the end of the day, a quiet consensus emerged behind closed doors. 3i Atlas was no longer acting like a passive body. It was behaving like a system, not alive, not artificial, not yet defined. But something organized, something capable of coordinated internal change, was happening inside it. And the next set of scans, scheduled as the object moved into clearer atmospheric conditions, would reveal one more layer, one that no team was prepared to confront. The sky was clear over the northern stations when the next round of scans began. Atmospheric noise had dropped to one of its lowest levels of the month, a fortunate coincidence, or perhaps something far stranger in hindsight. With the improved clarity, the telescopes could finally push deeper into the faint halo surrounding 3i Atlas, a haze that for weeks had been dismissed as ordinary dust or residual coma material. But on this night, the halo did not behave like dust. As the instruments sharpened their focus, the halo's brightness curve flattened, then separated, splitting into 2 distinct layers. One remained static, consistent with a thin particulate field. The other shifted in perfect alignment with the object's 42-minute internal cycle. This meant the oscillation wasn't confined to the object itself. It was extending outward, altering the density or reflectivity of the halo in a synchronized wave that alone introduced questions no natural model could comfortably answer. But the real shock came when the polarization filters were applied. The inner halo reacted, light twisting at an angle that suggested the presence of a structured electromagnetic field, not chaotic, not diffuse, but organized. A field that pulsed outward in expanding rings, faint but mathematically precise. The first ring expanded at 0.98 kilometers per second, the second at 1.02 kilometers per second, the third at 1.01 kilometers per second. A near-perfect rhythm, broken only by micro-variations too small to influence the broader pattern. The team stared at the data. No comet, asteroid, or interstellar debris object had ever produced such behavior. Fields like these required energy, structure, and intent, whether natural or not. Yet the energy output measured was tiny, almost delicate, as if the system were testing itself or stabilizing. When the object entered its next low albedo phase, something even more extraordinary happened. Within the polarized scan, a faint geometry appeared, 3 intersecting arcs forming an imprint on the inner halo, not a symbol, not markings. More like the interference pattern from a resonating structure. the same way ripples overlap when multiple waves meet on water. The arcs were stable, they repeated every cycle, and each time, their alignment grew clearer. This was no random artifact. It was a signature, something embedded deep inside the object, now reaching the threshold of detectability. The discovery forced the analysts to revise the classification of 3I Atlas from anomalous object to something unprecedented, a system with internal resonance mechanisms capable of interacting with its environment. And as the excitement built across the monitoring network, a new notification appeared on the shared channel. The infrared array in Greenland had detected a temperature shift. It was barely a fraction of a degree, but it was rising. The Greenland infrared array reported the temperature shift with precision down to hundredths of a Kelvin. It was subtle, almost imperceptible, yet it matched the exact phase of the 42-minute cycle already observed in the albedo and radio data. Analysts initially hesitated to integrate the measurement, suspecting calibration drift or local interference, but repeated observations confirmed it. The temperature variation was real, synchronized, and global across the surface of 3I Atlas, not localized to a single spot. No natural interstellar object of comparable size and composition had ever displayed this type of coordinated thermal pattern. Standard thermal inertia models predict diurnal heating and cooling along predictable lines, influenced mainly by rotation and distance from the Sun. But 3I Atlas was far beyond typical solar influence for this magnitude of variation. Its surface should have exhibited a slow, predictable cooling curve, yet it oscillated rhythmically in step with its internal 42-minute cycle. The implication was stark. Some mechanism inside the object was actively controlling energy distribution. A passive body cannot produce global temperature oscillations with such consistency. Something was modulating the heat output, intentionally or as a byproduct of internal activity. The thermal pulse appeared to radiate outward, affecting both the halo and the polarized electromagnetic field. All three phenomena, the albedo oscillations, the radio line, and the thermal shift, were now clearly linked, operating as a single coordinated system. By this point, the drift in the trajectory could no longer be considered in isolation. The positional anomaly was part of a larger set of behaviors, a signature of internal activity influencing external motion. Models recalculated with hypothetical internal forces showed that even minor cyclical energy outputs could generate measurable accelerations over weeks. In other words, the trajectory shift was a downstream effect of internal dynamics, rather than an external collision or gravitational perturbation. This realization reframed the investigation entirely. 3I Atlas was not simply off course, it was active. Its drift, once a curious positional deviation, was now a visible indicator of something occurring inside the object, interacting with both light and electromagnetic fields in measurable ways. Teams began cross-referencing historical observations. Weeks earlier, minor irregularities in the light curve, previously attributed to instrumental noise, suddenly gained significance. They may have been early signs of the emerging internal process, a slow awakening only now reaching observable thresholds. As the pattern became undeniable, the focus shifted to its implications. The 42-minute cycle, the coordinated thermal pulses, the polarized halo, taken together, suggested a level of internal organization unprecedented for a body classified as an interstellar asteroid. Standard models of mass, composition, and structure failed to account for the behavior. 3I Atlas could no longer be treated as inert. It had properties more akin to a self-regulating system. And as analysts digested this, they confronted the next question. If the object's internal processes are capable of generating measurable external effects, could they also explain the persistent drift in its trajectory? Could the cumulative energy output, although small in absolute terms, act as a continuous force nudging the object along a path inconsistent with gravitational predictions? Preliminary calculations suggested it could. Even a minor asymmetry in emitted energy, thermal, electromagnetic, or otherwise, applied in a consistent direction over weeks or months would be sufficient to account for the arc's second-level displacement observed. The positional anomaly was no longer an isolated puzzle. It was a symptom of a broader, internally driven phenomenon. And as the night drew on, a chilling yet precise realization formed. all the previous models, all the predictive frameworks had assumed passivity. 3i Atlas had been classified based on inertia and composition alone. The emergence of coordinated internal activity rendered every prior assumption incomplete. By the end of the observation cycle, the teams were left with a single undeniable truth. The object was alive with processes previously unseen, its internal mechanisms subtly, but measurably influencing every aspect of its interaction with the surrounding space. The focus then shifted toward predictive modelling. If the 42-minute cycle governs trajectory and environmental interaction, then future displacements could be anticipated. Provided the phase of the cycle is known, preliminary projections suggested that the cumulative drift would continue along the observed vector, gradually increasing unless the internal rhythm changed. This insight provided a rare tool, a way to predict movement not through traditional orbital mechanics alone, but by incorporating the object's internal dynamics. Yet even with these models, unanswered questions persisted. What is the origin of the 42-minute cycle? Is it purely a physical resonance, a structural oscillation, or something more complex? Could the internal process be self-sustaining indefinitely, or does it require interaction with its environment to maintain timing? And critically, what does this tell us about the nature of 3i Atlas itself, its formation, composition, and internal architecture? Spectral analysis was revisited in this context. The narrow near-infrared absorption feature detected earlier, previously attributed to surface change, was now interpreted as a response to the internal oscillator's pulsed energy. As energy redistributed internally, it subtly altered the object's emissivity, producing the transient absorption detected by the infrared spectrometers. This observation linked the internal rhythm, spectral feature, and environmental interaction in a coherent chain, supporting the system-level model of 3i Atlas. The modelling teams then considered environmental damping. Normally, oscillatory processes in isolated celestial bodies decay over time due to radiation loss or internal friction. Yet the primary 42-minute cycle had remained stable for weeks. Either the object's internal mechanism replenished energy actively, or it operated in an exceptionally low damping environment. Both possibilities were unusual but not impossible. Extremely rigid or resonant internal structures could maintain oscillations with minimal loss, particularly in the near vacuum of interstellar space. Attention returned to the trajectory. Applying the modelled internal forces to the object's predicted path produced a remarkable result. The calculated drift closely matched the observed displacement. Minute, continuous forces, synchronized with the internal cycle and amplified slightly by halo interactions, could fully account for the deviation without invoking unknown external perturbations. In other words, the system was self-consistent. Internal processes explained both the observed emissions and the motion anomaly. This conclusion reframed the investigative perspective. 3i Atlas was no longer simply off course. It was an active, self-modulating system, internally driving its behaviour and subtly influencing its surroundings. Every data point, from positional offset to polarised halo structure to thermal pulse, was now interpreted as a coordinated manifestation of this internal process. The 42-minute rhythm had become the central key to understanding both the present state and future behaviour of the object. Finally, the teams considered long-term predictions. If the internal cycle persisted unchanged, the trajectory drift would continue along its observed vector, gradually increasing. Minor secondary oscillations would produce small variations in amplitude and direction, but the overall pattern would remain predictable. However, any alteration to the internal mechanism, whether a damping event, a structural shift, or an interaction with interstellar medium, could disrupt the rhythm, causing measurable changes in both emissions and motion. The system was delicate. Small internal perturbations could manifest as observable anomalies externally. By the end of the observational cycle, the understanding of 3i Atlas had shifted completely. It was no longer a passive interstellar object, subject solely to gravitational forces. It was an internally active, self-regulating system, producing synchronized signals across multiple physical domains and capable of influencing its trajectory through subtle, continuous forces. The next step for the investigation would be to explore the origin of this internal rhythm, its physical mechanism, and the broader implications for interstellar object classification. The 42-minute cycle was not merely a curiosity, it was the defining characteristic of a fundamentally new class of celestial object, one that challenges conventional assumptions about inert interstellar bodies. And as this phase of study concluded, a single unresolved question remained. If 3i Atlas is capable of maintaining internal processes that influence motion and environment, how far can those processes extend, and what limits define their scope? The answer would guide the next chapter of observation, and potentially reveal behaviours that had never before been witnessed in space. The question of scope quickly became central to planning the next observational campaign. If 3i Atlas's internal processes could produce measurable effects on its immediate halo and trajectory, then the natural question was how far those effects could propagate. Observatories extended their monitoring to longer wavelengths, searching for faint signals that might indicate interactions with the sparse interstellar medium. Early results were striking. Even at distances of tens of thousands of kilometers from the object, subtle alignments in charged dust grains were detectable. These alignments oscillated in phase with the 42-minute cycle, confirming that the internal process was not confined to the object's surface or immediate halo. The system exerted influence well beyond its physical boundary, creating a structured dynamic field in space. Analysts then examined the radio data in this context. Previously, the narrowband emissions had been treated as isolated signals, but when mapped over the expanded spatial field, a faint but coherent extension became visible. The emissions were not simply radiating outward isotropically, they exhibited directional structure, with intensity diminishing along predictable vectors. This suggested that the object's internal oscillator could selectively channel energy, producing a patterned radiation field extending outward for at least several thousand kilometers. The implications for trajectory analysis were profound. If the internal system could couple with the surrounding environment, then the observed drift might not be solely due to direct recoil from internal energy pulses. Interactions with dust and plasma could amplify or redirect the force, subtly altering the motion in ways previously unaccounted for. In essence, the object was no longer isolated, it was part The focus now turned to the internal mechanism itself. Analysts began considering what types of structures could generate the observed 42-minute rhythm. With such consistency, standard models, solid, homogeneous bodies composed of rock and metal, were inadequate. Any oscillation of the magnitude and precision detected would typically require either highly specialized structural resonances or an organized system of interacting components, something entirely foreign to conventional interstellar object models. Thermal modelling suggested that a homogeneous body could not sustain the amplitude of the thermal pulse without exceeding the limits of surface material conductivity. Heat would diffuse unevenly, damping the cycle within hours. The observed persistence implied either a layered structure with insulating regions or an active redistribution system within the object, something capable of controlling energy flow and maintaining phase coherence. Rotation and mass distribution were reanalyzed. The object's spin period of 12.8 hours was nearly orthogonal to the 42-minute cycle. This confirmed that the oscillation was independent of the gross rotation, ruling out rotational modulation as the driver. Mass asymmetry could theoretically produce minor torques, but the forces involved were far too weak to account for the coordinated effects observed across trajectory, halo polarization, and thermal emission. Electromagnetic modelling offered further insight. The structured halo, with its concentric polarized rings, indicated a self-generated magnetic or electromagnetic field. Field strength was weak but consistent, and the pattern matched the pulse frequency. This suggested that the internal process could include an energy conversion mechanism, channeling stored or generated energy into a controlled electromagnetic output. Coupled with thermal redistribution, this mechanism could generate both observable pulses and slight persistent accelerations. The subcycles, the 20-minute and 70-minute variations, hinted at a multi-layered internal system simulations, demonstrated that a single oscillator could not produce these secondary patterns without interference or phase drift. The implication was a hierarchical system, possibly multiple interacting oscillators or nested resonance structures, each influencing the amplitude and phase of the primary cycle. This multi-layer resonance could explain the environmental effects observed. From halo structuring to subtle trajectory, drift spectral analysis provided additional constraints. Absorption features in the near-infrared indicated periodic changes in surface or near-surface material properties, likely tied to the internal oscillator's energy redistribution, emission strength, phase alignment, and polarization, all pointed to a system-wide integration of energy pathways, with the internal process modulating both surface properties and the surrounding environment. Environmental coupling remained a critical factor. The object's halo, initially dismissed as dust, was now understood as an extension of the system's influence. The synchronized oscillations in halo density and polarization demonstrated that the internal rhythm could propagate beyond the solid body, interacting with sparse interstellar material and producing measurable effects on both optical and radio signals. Trajectory modelling confirmed the connection. Simulated forces derived from internal energy pulses, when combined with halo interactions, accurately reproduced the observed drift. This integration of internal and external phenomena provided a self-consistent explanation for the previously anomalous position deviations. The remaining question was origin. How could such a complex, internally coordinated system arise? Known processes of interstellar object formation do not produce structures capable of self-regulated multi-domain oscillations. Either 3I Atlas is a rare, naturally evolved object with unique internal architecture, or it represents a class of interstellar bodies previously unrecognized, objects capable of internal processes that influence their environment in measurable ways. As the team prepared the next phase of observation, the internal oscillator emerged as the central mystery. Understanding its physical basis, energy source, and structural requirements became critical not only for predicting future behavior, but for redefining the scientific framework through which 3I Atlas and similar objects are classified. And so the investigation shifted fully inward, from trajectory, halo, and emissions back to the beating heart of the object itself, seeking the mechanism sustaining the 42-minute rhythm that now governs everything observable about 3I Atlas. With the investigation focused on the internal oscillator, teams turned to comparative analysis. They began reviewing data from past interstellar visitors, searching for subtle hints of similar behavior. Minor anomalies in brightness, thermal emission, or trajectory had often been dismissed as noise or observational error, but the precision and consistency observed in 3I Atlas suggested that prior measurements might contain overlooked evidence of analogous internal processes. Each candidate object was re-evaluated using the framework developed for 3I Atlas. Data gaps, lower resolution, and limited spectral coverage made definitive conclusions difficult, but faint correlations emerged. Some interstellar bodies displayed slight periodic thermal variations, minor trajectory deviations, or ephemeral polarization in surrounding dust halos. None were as pronounced or synchronized as 3I Atlas, yet they hinted at the possibility of a previously unrecognized class of dynamic interstellar systems. Meanwhile, simulations of the internal mechanism were refined. Multi-layer oscillators, resonant cavities, and anisotropic thermal and electromagnetic pathways were modelled to assess their ability to sustain long-term phase coherence. The models demonstrated that even small energy storage systems, if coupled correctly, could maintain oscillations across multiple domains indefinitely. Energy input could be minimal relative to total mass, yet sufficient to produce the observable effects in trajectory, albedo, and halo polarization. The environmental implications grew increasingly clear. Halo interactions and low-density interstellar medium coupling were not mere side effects. They were integral components of the system's dynamics. Each pulse influenced surrounding material, which in turn subtly reinforced the object's trajectory and oscillation. This feedback loop provided a natural explanation for the persistent drift and the spatial coherence of halo structures. 3i Atlas was not only internally active, it was externally resonant, its influence extending far beyond the visible surface. Analysts also began considering stability limits. The 42-minute primary cycle showed remarkable resilience, but simulations suggested that perturbations, such as collision with a minor particle stream or strong solar wind fluctuations, could introduce phase shifts. These shifts could temporarily alter both the timing of emissions and the trajectory vector. Observations to date, however, revealed no such disturbances, indicating that 3i Atlas had so far maintained an unusually stable environment. In its interstellar transit, secondary cycles were also modelled in more detail. The 20-minute and 70-minute subcycles appeared to modulate amplitude rather than phase, acting as internal calibrations for the primary oscillator. This hierarchical structure allowed the system to maintain overall coherence while compensating for minor energy dissipation, further explaining the exceptional precision observed in emissions and environmental influence. As the multi-domain model solidified, a deeper question emerged. What structural or material basis could support such an oscillator? Standard rock-metal interstellar objects could not sustain the observed phenomena. Simulations suggested possibilities such as layered composites, with varying density, embedded resonant chambers, or anisotropic conductive networks. Each could theoretically store and redistribute energy efficiently, but none had been observed in natural interstellar bodies with certainty. The trajectory models were updated accordingly. When internal pulses, halo interactions, and subcycle modulations were incorporated, the predicted drift matched observed positions with remarkable accuracy. The non-gravitational component of motion, previously unexplained, was now fully accounted for by the internal dynamics and environmental coupling. By the end of this phase, the conceptual model of 3i Atlas had transformed. It was no longer an inert visitor drifting through the solar system. It was a self-regulating system, internally oscillating, externally coupled, and capable of measurable influence over both its immediate halo and its broader trajectory. The next step in the investigation would focus on direct measurement of internal processes. High-resolution thermal imaging, synchronized multi-wavelength spectroscopy, and detailed polarization mapping were planned to capture finer details of energy distribution, phase relationships, and environmental influence. And as preparations began, one inescapable realization guided the teams. Understanding the internal rhythm, the 42-minute heartbeat, was not merely an exercise in curiosity. It was the key to predicting the system's behavior, anticipating environmental interactions, and perhaps redefining the fundamental classification of interstellar objects. 3i Atlas was not just anomalous. It was a prototype of a dynamic, self-organizing celestial system, and every observation moving forward would need to consider the full extent of its internal and external orchestration. The focus on direct measurement required unprecedented coordination across observational platforms. Optical telescopes were synchronized with radio arrays and infrared spectrometers, creating a network capable of continuous high-resolution monitoring. Each instrument contributed a unique perspective. Optical arrays mapped albedo variations, radio dishes tracked narrow-band emissions, and infrared spectrometers captured thermal fluctuations. Together, they provided a holistic view of 3i Atlas as a single integrated system. Early results from this synchronized campaign revealed finer structures within the halo polarization maps, showed that the previously observed concentric rings were not uniform. They contained subtle nodal patterns that shifted with each cycle. These nodes appeared as regions of intensified polarization, moving outward from the object's surface in a predictable sequence. Analysts interpreted them as manifestations of the internal oscillator's energy being propagated outward, modulating the halo in structured waves. Thermal mapping offered equally compelling evidence. Previously, infrared data indicated global surface pulses. but with continuous monitoring, analysts identified localized hotspots that expanded and contracted in phase with the primary cycle. These micro-variations suggested that the internal energy distribution was not uniform, but dynamically adjusted across regions within the object. The subcycles appeared to fine-tune these variations, maintaining overall phase coherence while compensating for minor dissipation or structural irregularities. Radio observations also advanced. The narrowband spike detected weeks earlier was now resolved into a more complex pattern, showing sidebands and harmonics corresponding precisely with the 42-minute cycle and its subcycles. The harmonics indicated that the object's internal system was capable of producing structured electromagnetic output, not merely a single pulsed emission. Directional mapping suggested the energy was being channeled along specific axes, reinforcing the notion of an organized internal mechanism capable of influencing both trajectory and environment. Integration of the three data streams provided the first quantitative measure of internal energy transfer. Analysts estimated that even modest energy shifts within the object could generate micronewton forces sufficient to produce the observed cumulative drift. Coupled with environmental interactions, halo structuring, dust alignment, and electromagnetic feedback, the model fully accounted for the trajectory deviation without invoking external perturbations. Simulations extended to hypothetical interactions with interstellar medium particles. Even at extremely low densities, the structured fields of 3I Atlas produced coherent alignments in charged dust grains and plasma particles. These interactions, although subtle, confirmed that the object's influence extended well beyond its visible boundary, forming a dynamic, oscillating envelope around the system. The halo was not simply a passive feature, it was an active component of the system's overall behaviour. Further modelling examined system resilience. Phase stability of the 42-minute cycle persisted even under minor perturbations, including simulated microcollisions with dust and variable solar wind flux. The subcycles acted as internal compensators, dynamically adjusting amplitude and ensuring long-term coherence. This hierarchical oscillatory structure provided a plausible mechanism for maintaining the system's remarkable precision across multiple physical domains. Spectral measurements confirmed the connection between internal activity and surface properties. Periodic variations in near-infrared absorption corresponded to the internal pulse, demonstrating a direct link between energy redistribution within the object and observable external effects. Each pulse subtly altered emissivity, halo density, and even the polarization pattern, reinforcing the conclusion that 3I Atlas was a fully integrated, internally active system. By the conclusion of this observation phase, 3I Atlas had been definitively characterized: a multi-domain oscillator, internally active, externally coupled, and capable of measurable influence over both trajectory and surrounding environment. Its 42-minute cycle governed behavior across light, radio, and thermal domains, while subcycles fine-tuned the process, maintaining phase coherence and environmental interactions. The next stage of inquiry would involve direct modelling of internal structure. What configuration of mass, density, and conductive pathways could sustain such coordinated oscillations indefinitely? How did energy transfer between internal subsystems, surface layers, and environmental fields? And crucially, could the internal mechanism evolve over time, adjusting the cycle in response to environmental or internal changes? Understanding these mechanisms would not only explain current behaviour, but also allow predictions of future trajectory, emissions, and environmental interactions. 3I Atlas had become a prototype for a previously unrecognised class of interstellar objects, internally active, self-regulating systems whose influence extends beyond their immediate physical boundaries. And as the next observational campaign was prepared, one truth had become undeniable. The 42-minute rhythm was the defining feature of this system, the key to decoding the extraordinary processes driving 3I Atlas through space. Every pulse, emission, and drift was a measurable expression of that rhythm, and understanding it would unlock the full nature of this unprecedented object. With the 42-minute rhythm established as the central governing process, the investigation turned toward potential energy sources sustaining it. Analysts first considered radioactive decay within the object's core. While theoretically capable of providing steady, long-term energy, decay rates and elemental abundances could not account for the rapid, phase-coherent oscillations observed across multiple domains. The subcycles, fine amplitude adjustments, and environmental coupling required a mechanism far more dynamic than passive decay. Next, attention shifted to mechanical and structural possibilities. Layered internal structures, differing densities, embedded cavities, or resonant chambers could in principle store and redistribute energy efficiently. Simulations demonstrated that even modest internal motion, channeled through resonant cavities, could produce measurable effects externally. Thermal pulses could be directed, electromagnetic fields could be modulated, and trajectory drift could emerge naturally as a byproduct of asymmetrically applied forces. The object could function as a self-contained energy redistribution system, a coherent mechanism translating internal dynamics into external influence. Analysts also considered rotational coupling. Although the 12.8-hour spin did not align with the 42-minute cycle, it could serve as a baseline for energy distribution interactions between rotational inertia and internal oscillators might stabilize the primary rhythm, while subcycles fine-tuned output across the surface and halo. This combination could explain the exceptional phase coherence observed over multiple weeks, maintaining consistency even under minor environmental perturbations. Multi-domain data reinforced the hypothesis. Optical albedo variations corresponded precisely with thermal pulses and radio emission spikes. Polarized halo patterns shifted predictably with the cycle, confirming that the internal process was propagating outward in a coordinated manner. This systemic integration indicated not only energy redistribution, but environmental modulation. The halo, dust, and sparse plasma were being influenced in phase with internal oscillations. Trajectory modeling confirmed that even small internal forces could account for observed drift. Micronewton accelerations generated by internal pulses, amplified through halo and environmental interactions, reproduced arc-second level positional deviations over weeks. The object's drift, previously classified as anomalous, was now predictable, a direct consequence of internal oscillation propagated into its surrounding medium. Further observations revealed additional substructures within the halo. Nodes of increased polarization intensity shifted outward with each cycle, forming faint interference patterns consistent with energy propagation from a central oscillator. Thermal imaging showed concentric hotspots expanding and contracting in sync, suggesting that energy redistribution was not uniform but dynamically controlled, with localized regions responding to internal pulses and sub-cycle modulation. Spectroscopy provided additional confirmation. Near-infrared absorption features varied predictably with each pulse, linking internal energy shifts to surface and environmental properties. These observations reinforced the model of 3i Atlas as a multi-domain system, internally active, externally coupled, and capable of producing coordinated, measurable effects on both motion and surrounding space. The hierarchical structure of oscillations, the primary 42-minute cycle, and secondary subcycles emerged as a critical feature. This arrangement allowed the object to maintain long-term stability while compensating for energy dissipation and minor environmental fluctuations. The system's resilience suggested a sophisticated mechanism capable of sustaining precise coordinated oscillations over extended periods. As observational campaigns progressed, the team began developing predictive models. Using the known phase relationships between optical, thermal, and radio data, they could forecast future pulse timings, halo configurations, and subtle trajectory shifts. This predictive capability represented a breakthrough. For the first time, an interstellar object's behavior could be anticipated not solely through orbital mechanics, but through an integrated understanding of internal dynamics. By the conclusion of this phase, 3i Atlas had been definitively characterized as an unprecedented class of celestial system, internally oscillating, environmentally coupled, and capable of measurable influence across multiple domains. Its 42-minute rhythm, reinforced by hierarchical subcycles, governed behavior across light, thermal, and electromagnetic signatures, while subtly shaping its trajectory through interaction with surrounding space. The next challenge was structural. What physical configuration within 3i Atlas could sustain the system indefinitely? Could internal cavities, anisotropic materials, or layered conductive pathways maintain precise oscillations over months or years? Understanding this would reveal not only the mechanism behind current behavior, but also the potential limits and evolution of the system. And as preparations began for the next high-resolution observational campaign, one reality became inescapable. The 42-minute cycle was the heartbeat of 3i Atlas. Every emission, every shift, every pulse was an expression of that rhythm, and understanding it fully was the key to unlocking the object's extraordinary internal and external processes. As the investigation moved deeper into structural modelling, analysts faced the challenge of reconciling observed phenomena with plausible internal architecture. Any candidate mechanism needed to satisfy several constraints simultaneously. It had to sustain the 42-minute primary cycle, accommodate the 20 and 70-minute subcycles, produce measurable thermal, optical and radio effects, and influence the surrounding environment without external energy inputs beyond minimal background radiation. Conventional rock metal interiors could not meet these requirements. Layered compositional models offered one potential solution. By hypothesizing alternating strata of conductive and insulating materials, simulations demonstrated that energy could be stored, channeled, and released rhythmically. Embedded cavities or resonant chambers could amplify these oscillations, producing concentrated pulses in electromagnetic and thermal domains. In this configuration, minor asymmetries could translate to directional forces, accounting for the observed trajectory drift. Finite element modelling of such structures produced promising results. Energy input, even if minimal, could propagate through the system in controlled waves, producing synchronized surface heating, albedo oscillations, and halo polarization effects. The phase coherence of the 42-minute cycle was maintained through feedback between layers, while secondary subcycles fine-tuned amplitude modulation. The system functioned as a multi-domain oscillator, distributing energy internally while projecting influence outward. Environmental interactions were reanalyzed in this structural context. The halo, previously assumed passive, was now understood as an extension of the object's internal dynamics. Polarization patterns, dust alignment, and faint infrared signatures were consistent with energy radiating from the internal system, interacting with sparse interstellar particles and producing measurable effects on surrounding space. The environment was not merely reactive, it was coupled to the internal oscillator, forming a dynamic, self-regulating system. Trajectory simulations incorporated these mechanisms. Directional energy emissions from internal structures, combined with feedback from halo interactions, reproduced the observed positional drift with remarkable accuracy. The arcsecond level displacement, once considered anomalous, now appeared as a natural consequence of the coordinated system. Even minor perturbations, such as collisions with microparticles, produced phase adjustments, but did not disrupt overall coherence, demonstrating the system's resilience. Spectral analysis provided additional insight. Near-infrared absorption variations coincided with pulse timing, linking internal redistribution of energy to surface properties and halo behavior. These correlations reinforced the model of 3i Atlas as an integrated system in which internal oscillations directly modulate external manifestations, from electromagnetic emissions to halo structuring and thermal patterns. The hierarchical organization of oscillations became increasingly apparent. The 42-minute primary cycle governed overall timing and energy distribution, while the 20 and 70-minute subcycles provided fine adjustments, maintaining phase stability despite energy dissipation and environmental interactions. This nested structure allowed precise control of internal and external dynamics, ensuring that trajectory drift, halo patterns, and emission pulses remained synchronized over extended periods. With these models, predictive capability improved dramatically. By tracking the phase of the primary cycle and subcycles, future albedo minima, radio spikes, thermal pulses, and subtle trajectory shifts could be forecast with unprecedented precision. Observatories could now plan coordinated multi-wavelength observations, capturing each pulse across optical, infrared, and radio domains simultaneously. By the end of this phase, 3i Atlas had been confirmed as a system unlike any previously observed interstellar object. Internally oscillating, environmentally coupled, and multi-domain active, it was capable of influencing both its immediate surroundings and its trajectory through coordinated energy redistribution. The 42-minute rhythm had become the central organizing principle, with hierarchical subcycles ensuring stability, phase coherence, and environmental modulation. The next investigative frontier would be direct constraints on internal architecture, material composition, cavity structures, and energy storage mechanisms. Understanding these components was critical not only for explaining current behavior, but for anticipating long-term evolution, potential phase shifts, and trajectory changes. And as preparations for high-resolution internal modelling advanced, one reality became increasingly clear. Every measurable aspect of 3i Atlas, from its pulse to its halo to its drift, was a reflection of the internal rhythm. The 42-minute cycle was not simply a pattern, it was the system's operating principle, the key to decoding an unprecedented cell with internal architecture. Now the primary focus, the team explored material and structural hypotheses capable of sustaining long-term multi-domain oscillations. Models suggested that purely homogeneous, rock-metal compositions could not account for the observed precision. Instead, a hybrid interior with alternating layers of differing conductivity, density, and rigidity could store energy efficiently and redistribute it rhythmically. Embedded resonant chambers could amplify and direct energy flows, producing the coherent thermal, optical, and electromagnetic outputs observed. Finite element simulations demonstrated that even modest energy inputs could maintain phase coherence indefinitely if routed through such a structured interior. Thermal pulses could be localized or global, surface albedo could oscillate predictably, and directed electromagnetic emissions could be generated, all in sync with the 42-minute primary cycle. Subcycles at 20 and 70 minutes acted as internal modulators, fine-tuning energy release to preserve overall rhythm despite minor losses or environmental perturbations. Environmental coupling remained a central consideration. Sparse interstellar particles, dust, plasma, and low-density gas were visibly influenced by the system halo polarization patterns, and subtle alignment of dust grains followed the primary cycle with remarkable fidelity. These interactions were not incidental. They represented a feedback loop. Energy propagated from the internal oscillator shaped the halo, and the resulting particle alignment and electromagnetic interactions produced measurable forces, contributing incrementally to trajectory drift 3. 3i Atlas was effectively a system extending beyond its physical boundary, a dynamic interplay between internal oscillation and environmental modulation. Trajectory models incorporated these forces. Calculated accelerations arising from rhythmic energy emission and halo interaction precisely matched observed deviations, micronewton-scale impulses, consistent with the internal oscillator's output, produced cumulative shifts observable over weeks. In other words, the object's drift was a direct consequence of its internal and environmental system, not an anomalous external influence. Thermal mapping reinforced the concept of controlled energy redistribution. Hotspots on the surface expanded and contracted in phase with the primary cycle, while secondary subcycles modulated amplitude regionally. Infrared absorption features varied predictably, indicating that energy was being actively directed across surface layers. These variations also correlated with observed radio emission harmonics, confirming cross-domain synchronization. Spectroscopic analysis further constrained possible internal structures. Variations in emissivity aligned with pulse timing, suggesting that internal energy flows affected material properties across the object. The structural model had to allow for both energy storage and dynamic redistribution. With internal pathways capable of converting stored energy into synchronized output across optical, thermal, and electromagnetic channels, simulations explored stability limits. Minor perturbations, microcollisions, dust impacts, or fluctuations in solar wind produced phase adjustments but did not disrupt the system. The hierarchical oscillator structure absorbed these perturbations, maintaining coherence. This explained the long-term persistence of the 42-minute cycle and its subcycles despite the harsh conditions of interstellar space. Predictive modelling became increasingly robust. By tracking the phase of the primary cycle and subcycles, the timing of albedo minima, radio spikes, thermal pulses, and trajectory deviations could be forecast with high accuracy. Coordinated multi-wavelength observation campaigns could now capture every aspect of 3i Atlas's behavior in real time, confirming the interconnected nature of its internal and external processes. By the conclusion of this modeling phase, 3i Atlas was established as a fully integrated, internally active, and environmentally coupled system. The 42-minute rhythm and its subcycles governed behavior across multiple domains, influencing both observable emissions and trajectory. The system was resilient, self-regulating, and capable of extending its influence into surrounding space. The next critical step would be to refine constraints on internal architecture, identifying plausible material compositions, cavity structures, and energy pathways, and determining how these features could maintain the system's remarkable coherence. Understanding the internal mechanism was essential not only for explaining current phenomena, but for predicting the future evolution of this unprecedented interstellar system. And as preparations for these high-resolution internal studies advanced, one undeniable truth became central to the investigation. The 42-minute cycle was the operating principle of 3i Atlas. Every emission, every pulse, every drift was a direct manifestation of that rhythm. Decoding it fully would reveal the fundamental nature of this extraordinary celestial object. With the focus now squarely on internal constraints, the team turned to energy budgeting and sustainability. Any plausible internal mechanism had to operate within the limits of the object's mass, composition, and environment. Radioactive decay alone was insufficient, and ambient interstellar radiation offered negligible input. Models indicated that energy must be efficiently stored, recycled, and redistributed internally. Layered structural models provided a potential solution. By alternating high conductivity and insulating layers, energy could be accumulated and channeled into rhythmic pulses. Simulations suggested that embedded cavities could act as resonant chambers, amplifying oscillations while maintaining phase coherence. These chambers would allow energy to flow selectively, producing the observed thermal, optical, and electromagnetic patterns. The hierarchical subcycles were key to maintaining stability. The primary 42-minute cycle controlled overall timing, while 20 and 70-minute subcycles adjusted amplitude locally, compensating for dissipative losses and environmental influences. This structure created a robust internal metronome, resilient even under minor perturbations such as microcollisions or variations in solar wind density. Environmental coupling remained a central component. Polarization mapping of the halo showed nodal patterns moving outward in sync with internal pulses. Infrared observations revealed concentric thermal waves propagating into surrounding dust and plasma. These effects were not incidental. They represented a two-way interaction. Energy from the internal oscillator influenced the environment, and feedback from the environment reinforced trajectory stability. The system extended far beyond the object's physical boundary, forming a dynamic, multi-layered envelope. Trajectory simulations incorporated both internal and environmental forces. Even micronewton-scale impulses from rhythmic energy release, combined with interactions in the halo, could reproduce the observed arc-second-level drift. The cumulative effect over weeks matched the measured deviations precisely, confirming that 3i Atlas's motion was an emergent property of its internal and external dynamics. Spectroscopy provided further insight. Periodic variations in near-infrared absorption aligned with pulse timing, demonstrating that internal energy shifts directly modulated surface and near-surface properties. Corresponding variations in radio emission confirmed cross-domain synchronization. Energy redistribution within the object produced measurable changes in optical, thermal, and electromagnetic outputs, illustrating the integrated nature of the system. Predictive modeling became increasingly accurate. By tracking the phase of the primary cycle and subcycles, the timing of thermal pulses, albedo minima, radio spikes, and subtle trajectory shifts could be forecast reliably. Coordinated observation campaigns were able to capture multi-domain data simultaneously, confirming the validity of the system-level model. The next step involved structural inference. Material composition, cavity placement, and conductive pathways were modeled to understand how the internal mechanism could maintain coherence over months. Simulations indicated that a layered interior with resonant cavities and anisotropic pathways could sustain the 42-minute rhythm while producing subcycle modulation, environmental coupling, and measurable trajectory influence. By the end of this phase, 3i Atlas had been definitively characterized as a self-regulating, internally active, environmentally coupled system. The 42-minute rhythm governed its behavior across all measurable domains. Subcycles fine-tuned amplitude and phase, while environmental interactions reinforced coherence and contributed to trajectory adjustments. The forthcoming investigations would focus on direct constraints on internal architecture and energy pathways, refining understanding of how 3i Atlas maintains its extraordinary coordination. And as the teams prepared for these next observations, one truth became increasingly clear. The 42-minute cycle was the operating principle of the system. Every pulse, emission, and drift was a measurable manifestation of that rhythm, and fully decoding it was essential to revealing the true nature of this unprecedented celestial object. With internal architecture now the central focus, attention shifted to detailed modelling of energy transfer and oscillatory dynamics. Analysts sought to determine how the 42-minute primary cycle could be sustained over weeks, and how the 20 and 70-minute subcycles could modulate amplitude and phase without significant loss. Standard models of solid interstellar bodies offered no solution. Internal mechanisms had to be highly organised and exceptionally efficient. Layered compositional structures emerged as the most plausible model. Alternating strata of high conductivity and insulating materials allowed energy to be stored and channeled selectively. Embedded cavities acted as resonant chambers, amplifying oscillations while maintaining precise phase relationships. Thermal energy, electromagnetic pulses, and mechanical vibrations could all be redistributed internally, producing the coordinated multi-domain effects observed. Finite element simulations supported this configuration. Even minimal energy input, if routed properly through layered structures and resonant cavities, could produce the rhythmic outputs observed. Localized thermal pulses, albedo oscillations, and narrowband radio emissions, all aligned with the 42-minute primary cycle subcycles, provided fine-tuning, dynamically adjusting amplitude to compensate for environmental damping or internal losses. Environmental coupling remained a critical aspect. Halo polarization maps revealed nodal structures moving outward in sync with the primary cycle. Infrared observations showed concentric thermal waves propagating into surrounding dust and plasma. These effects were not incidental. They formed a feedback loop. Internal oscillations influenced the environment, while environmental interactions reinforced the system's coherence, subtly affecting trajectory drift. The object's influence extended far beyond its physical surface, forming a dynamically coupled envelope with measurable physical effects. Trajectory modelling incorporated these internal and external forces, micronewton-scale impulses from rhythmic energy emission, when amplified by halo and environmental interactions, accurately reproduced observed arc-second-level displacements. The object's drift, once labelled anomalous, now emerged as a natural consequence of internal and environmental dynamics. Spectral data reinforced the internal-external connection. Near-infrared absorption features varied in phase with the oscillator, linking internal energy redistribution directly to surface and halo properties. Radio emission harmonics matched sub-cycle patterns, confirming cross-domain synchronization. Energy flow within the object directly modulated observable external phenomena, illustrating a fully integrated system. The hierarchical oscillator structure explained long-term stability. The primary 42-minute cycle governed global timing, while 20 and 70-minute subcycles modulated amplitude regionally. This arrangement allowed the system to absorb minor perturbations, micro-collisions, solar wind fluctuations, or dust interactions, without losing phase coherence. The internal metronome maintained synchronization across multiple domains, ensuring persistent trajectory effects and environmental modulation. Predictive capability improved as phase relationships were mapped. By monitoring the primary cycle and subcycles, the timing of thermal pulses, albedo minima, radio spikes, and trajectory deviations could be forecast precisely. Coordinated multi-wavelength campaigns captured each pulse simultaneously, confirming the validity of system-level models and providing unprecedented insight into an active interstellar object. The next investigative step focused on constraining internal architecture. Simulations explored combinations of material composition, cavity placement, and anisotropic pathways that could support long-term oscillations while producing multi-domain outputs. These models indicated that a layered, cavity-rich interior could sustain the 42-minute rhythm indefinitely, drive subcycle modulation, and maintain environmental coupling and trajectory influence. By the end of this phase, 3i Atlas was recognized as a fundamentally new type of interstellar system, internally active, environmentally coupled and hierarchically oscillatory. The 42-minute cycle was its defining rhythm. Sub-cycles ensured stability and fine control, and interactions with the environment extended its influence beyond its immediate surface. As the next observation phase was planned, one conclusion stood unchallenged. The 42-minute rhythm was the operating principle of 3i Atlas. Every pulse, every emission, every subtle drift in trajectory was a direct manifestation of this internal oscillator. Understanding it fully was essential to unlocking the true nature of this unprecedented sea. With the structural model of 3i Atlas increasingly refined, attention turned to potential limits and variability within the system. Analysts sought to determine how resilient the 42-minute primary cycle and its subcycles could be under prolonged exposure to interstellar conditions. Simulations suggested that even minor external perturbations, collisions with micrometeoroids, changes in solar wind flux, or variations in ambient plasma density, could induce phase shifts. Yet, the hierarchical oscillatory structure appeared capable of compensating for these disturbances, maintaining coherence across all observable domains. Material composition became a critical focus. For the internal oscillator to remain functional over extended periods, it required both thermal and electromagnetic conduction properties. Beyond those typical of standard rock-metal interstellar bodies, layered structures with alternating conductivity and density could channel energy efficiently, while embedded resonant cavities amplified oscillations without significant energy loss. These features allowed the system to maintain a precise rhythm across optical, thermal, and electromagnetic outputs, producing the synchronized effects observed in halo polarization, thermal pulses, and radio emission harmonics. Further environmental analysis revealed subtle yet measurable feedback mechanisms. Dust grains within the halo exhibited coherent alignment, following the primary cycle's timing with remarkable fidelity. Infrared mapping indicated that concentric thermal waves propagated outward, interacting with local plasma and dust to generate secondary effects, including minor adjustments in trajectory. These interactions confirmed that the object's influence extended beyond its immediate surface, creating a coupled system in which internal dynamics and environmental response reinforced one another. Trajectory modelling reinforced this integrated view. Micronewton impulses generated by internal energy redistribution, when coupled with halo interactions, reproduced observed deviations with high accuracy. The drift, once considered an anomaly, emerged as a deterministic outcome of the object's internal-external system. Phase tracking of subcycles allowed predictions of incremental shifts, demonstrating that even small-scale oscillatory processes could accumulate measurable effects over weeks or months. Spectral analysis continued to constrain the internal mechanism. Variations in near-infrared absorption and emission features matched both primary and secondary cycles, linking energy redistribution within the object to surface and environmental changes. Radio emission harmonics further confirmed the multi-domain coherence of the system. Energy flow within 3i Atlas was not confined internally. It directly modulated observable properties across multiple wavelengths, establishing a unified active system. Hierarchical oscillation models explained long-term stability. The primary cycle established global timing, while subcycles modulated amplitude locally, compensating for dissipative losses and environmental perturbations. This nested structure functioned as a self-regulating metronome, allowing the system to absorb minor disturbances without losing phase coherence or disrupting trajectory and halo behavior. Predictive models became increasingly precise. By tracking the primary cycle and subcycles, analysts could forecast thermal pulses, albedo minima, radio spikes, and incremental trajectory deviations. Coordinated observation campaigns, synchronized across optical, infrared, and radio domains, captured multi-domain pulses in real time, validating the hierarchical oscillator model. The next investigative focus was structural validation. Material composition, cavity placement, and anisotropic energy pathways were modelled to determine plausible configurations capable of sustaining the observed oscillatory behaviour indefinitely. Simulations indicated that a cavity-rich, layered interior could sustain the 42-minute rhythm, drive subcycle modulation, and maintain environmental coupling, all while producing measurable trajectory effects. By the end of this phase, 3i Atlas was fully recognized as an internally active, environmentally coupled, hierarchically oscillatory system. Its 42-minute rhythm defined the system, subcycles ensured stability and precise modulation, and interactions with the environment extended its influence beyond the physical body. As preparations began for targeted high-resolution observations and structural modelling, one principle remained clear. The 42-minute cycle was the heartbeat of 3i Atlas. Every pulse, emission, and subtle drift was a direct manifestation of this rhythm, and decoding it fully was essential to understanding the true nature, internal structure, and long-term behaviour of this unprecedented interstellar system celestial object, its structure, and its long-term behaviour in interstellar space. With the system's internal hierarchy and environmental interactions now firmly established, attention shifted to long-term observational predictions. Analysts recognized that understanding the 42-minute primary cycle and its subcycles was not only critical for decoding current behavior, but also essential for forecasting future states. By mapping phase relationships across optical, thermal, and electromagnetic domains, they could anticipate not only pulse timing but also subtle trajectory shifts weeks in advance. Environmental monitoring revealed additional layers of complexity. Sparse interstellar dust, plasma, and neutral gas within the halo responded consistently to internal oscillations. Polarization nodal structures propagated outward in sync with the primary cycle, while concentric thermal waves extended to distances previously considered irrelevant for dynamic influence. The system demonstrated a degree of self-organization. Internal pulses structured the environment, and environmental feedback stabilized the internal rhythm, creating a coupled, self-regulating system extending far beyond the visible boundary of 3i Atlas. Trajectory modelling continued to integrate these interactions. Micronewton impulses generated by the internal system, amplified through halo feedback, produced cumulative displacements that matched observed deviations precisely. The once anomalous drift now emerged as a predictable product of internal-external coupling. Hierarchical subcycles provided fine adjustments, ensuring that trajectory, halo polarization, and emission harmonics remained synchronized over extended observation periods. Thermal mapping added another dimension of understanding. Localized hotspots expanded and contracted in phase with the primary cycle, modulated by subcycles to maintain global coherence. Infrared absorption and emission features oscillated predictably, demonstrating that internal energy redistribution directly influenced surface and near-surface properties. These variations were mirrored in radio emissions, confirming cross-domain synchronization and reinforcing the concept of a fully integrated multi-domain system. Spectroscopic analysis further constrained internal hypotheses. Observed variations in emissivity, polarization, and emission intensity required a layered, cavity-rich internal architecture capable of both storing and distributing energy efficiently. Alternating layers of differing conductivity and density, combined with resonant chambers, could sustain the 42-minute rhythm while generating sub-cycle modulation, environmental feedback, and measurable trajectory influence simulations explored system resilience. Minor perturbations, including microcollisions, variations in interstellar medium density, and solar wind fluctuations, produced temporary phase adjustments but did not disrupt overall coherence. The hierarchical oscillator absorbed disturbances, maintaining synchronization across multiple domains and ensuring that both observable outputs and trajectory remained stable. Predictive modelling achieved unprecedented accuracy. By tracking the primary cycle and subcycles, analysts could forecast albedo minima, thermal pulses, radio spikes, and incremental trajectory shifts with high confidence. Multi-wavelength observational campaigns captured each pulse simultaneously, validating system-level models and confirming the integrated nature of internal and external processes. The next investigative frontier was direct inference of internal structure. Material composition, cavity placement, and energy pathways were modelled to identify plausible configurations capable of sustaining long-term oscillations. Simulations indicated that a cavity-rich, layered interior could support the 42-minute rhythm, modulate subcycles, and maintain environmental coupling while producing measurable trajectory effects. By the conclusion of this phase, 3i Atlas had been conclusively characterized as an internally active, environmentally coupled, hierarchically oscillatory system. The 42-minute primary cycle defined its behavior, subcycles, fine-tuned stability and modulation, and environmental interactions extended its influence well beyond its physical surface. As preparations for high-resolution structural observations progressed, one reality became unmistakable. The 42-minute rhythm was the heartbeat of 3i Atlas. Every pulse, every emission, every incremental drift was a measurable manifestation of this internal oscillator. Understanding it fully was essential to revealing the true nature, internal architecture, and long-term dynamics of this unprecedented interstellar system. With the system's internal and environmental dynamics now well characterized, attention turned to the implications of energy transfer and long-term sustainability. Analysts asked how the internal oscillator could maintain coherence across multiple domains over extended periods. Standard interstellar object models, homogeneous rock-metal bodies with passive thermal diffusion, could not account for the precision, phase stability, or multi-domain outputs observed in 3i Atlas. Layered internal models became central. Alternating strata of high conductivity and insulating materials provided both energy storage and directional pathways for redistribution. Embedded cavities acted as resonant amplifiers, allowing energy to propagate in controlled pulses. These structures enabled the 42-minute primary cycle to remain coherent, while subcycles dynamically adjusted amplitude, compensating for energy dissipation and environmental perturbations. The environmental system, far from passive, acted as an extension of the internal oscillator. Polarized halo structures and aligned dust grains responded predictably to internal pulses, creating measurable electromagnetic and optical effects. Infrared mapping revealed concentric thermal waves propagating outward, which interacted with sparse plasma and interstellar dust. These feedback interactions reinforced phase stability, subtly influencing trajectory and demonstrating that 3i Atlas functioned as a coupled system extending beyond its visible boundary. Trajectory modeling integrated internal and external dynamics, micronewton impulses generated by internal energy redistribution, amplified through halo interactions, reproduced observed arc second-level deviations. The drift, once considered anomalous, was now fully accounted for by the coordinated internal-external system. Hierarchical subcycles allowed fine adjustments, ensuring synchronization of trajectory, emissions, and halo polarization over weeks of observation. Thermal and spectroscopic data further constrained internal structure. Localized surface hotspots expanded and contracted in phase with the primary cycle, modulated by subcycles for global coherence. Near-infrared absorption and emission features tracked these pulses, linking internal energy redistribution directly to observable surface and halo properties. Corresponding radio emission harmonics confirmed multi-domain synchronization. Simulations explored system resilience. Minor perturbations, dust impacts, fluctuations in interstellar medium density, or variable solar wind produced temporary phase shifts but did not compromise overall stability. The hierarchical oscillator absorbed disturbances, maintaining coherence across optical, thermal, and electromagnetic outputs, while preserving cumulative trajectory effects. Predictive modeling matured. Phase tracking of the primary cycle and subcycles allowed accurate forecasts of thermal pulses, radio spikes, albedo minima, and incremental trajectory shifts. Coordinated multi-wavelength campaigns captured these events in real time, confirming the validity of the integrated hierarchical model and demonstrating that 3i Atlas's behavior could be forecast with unprecedented precision. The next investigative priority was structural inference. Material composition, cavity placement, and anisotropic energy pathways were modeled to determine plausible configurations capable of sustaining multi-domain oscillations indefinitely. Results suggested that a layered, cavity-rich interior could maintain the 42-minute rhythm, modulate subcycles, and drive environmental coupling while producing measurable trajectory influence. By the conclusion of this phase, 3i Atlas had been definitively characterized as an internally active, environmentally coupled, hierarchically oscillatory system. Its 42-minute primary cycle defined behavior across optical, thermal, and electromagnetic domains. Subcycles provided fine modulation, while environmental interactions extended the system's influence beyond the immediate body. As preparations began for targeted high-resolution structural studies, one principle stood unchallenged. The 42-minute rhythm was the operating principle of 3E Atlas. Every pulse, emission, and trajectory deviation was a measurable manifestation of this internal oscillator, and fully decoding it was essential to understanding the true nature, internal architecture, and long-term dynamics of this unprecedented interstellar system. As the investigation progressed, focus intensified on the potential long-term evolution of 3I Atlas's internal and external system. Analysts recognized that the 42-minute primary cycle and its sub-cycles, while currently stable, were not immune to cumulative effects over months or years. Even minor energy losses, shifts in environmental density, or micro-collisions could slowly alter phase relationships. Yet simulations indicated that the hierarchical oscillator was remarkably resilient. Sub-cycles acted as internal regulators, compensating for minor disturbances and maintaining phase coherence across optical, thermal, and electromagnetic domains. Material and structural modelling became increasingly sophisticated. Layered compositions with alternating conductive and insulating strata, combined with embedded resonant cavities, remained the most plausible architecture. These features allowed energy to be stored, amplified, and redistributed rhythmically, sustaining the 42-minute cycle while modulating amplitude through sub-cycles, thermal mapping, infrared absorption, and radio emission harmonics, all aligned with predictions from these structural models, reinforcing the validity of the proposed configuration. Environmental interactions continued to reveal deeper complexity. Polarization nodes within the halo shifted predictably with each cycle, while concentric thermal waves extended outward, interacting with dust, plasma, and neutral gas. These interactions created a coupled feedback loop. Internal pulses shaped the environment, and environmental response reinforced internal phase stability. Even minor trajectory adjustments were consistent with these dynamics, indicating that 3I Atlas's influence extended far beyond its visible surface. Trajectory modelling integrated these mechanisms fully. Micronewton impulses generated by internal energy redistribution, amplified by halo interactions, produced cumulative displacements that matched observed deviations precisely. The previously anomalous drift now appeared as a deterministic consequence of the coupled internal environmental system. Subcycles ensured fine control, maintaining synchronization across all measurable domains despite external perturbations. Spectral and thermal data reinforced these conclusions. Localized surface hotspots expanded and contracted with predictable timing, and near-infrared absorption features tracked these changes. Radio emission harmonics corresponded to subcycle patterns, demonstrating cross-domain synchronization and confirming that energy flow within 3I Atlas directly modulated both surface and environmental properties. Simulations of system resilience further highlighted the sophistication of the internal architecture. Phase adjustments absorbed minor disturbances without compromising overall coherence. Even under variable interstellar medium density, solar wind fluctuations, and micro-collisions, the hierarchical oscillator preserved global rhythm while fine-tuning localized energy outputs. Predictive modeling matured into a precise tool. By monitoring phase relationships, analysts could forecast thermal pulses, albedo minima, radio spikes, and incremental trajectory shifts with unprecedented accuracy. Coordinated multi-wavelength observation campaigns captured these events in real time, validating hierarchical models and confirming that the object's behavior could be predicted with high confidence. The next investigative step focused on direct structural inference. Simulations explored cavity placement, material composition, and anisotropic energy pathways required to sustain multi-domain oscillations over months or longer. Results suggested that a cavity-rich, layered interior could maintain the 42-minute rhythm, modulate subcycles, and drive environmental coupling while producing measurable trajectory effects. By the end of this phase, 3I Atlas was confirmed as an internally active, environmentally coupled, hierarchically oscillatory system. Its 42-minute primary cycle governed behavior across optical, thermal, and electromagnetic domains. Subcycles provided fine modulation and phase stabilization, while environmental interactions extended influence beyond the physical body. As preparations began for the next high-resolution study, one central principle remained clear. The 42-minute cycle was the heartbeat of 3I Atlas. Every pulse, emission, and drift in trajectory was a direct manifestation of this rhythm. Fully decoding it was essential to understanding the object's internal architecture, its long-term behaviour, and the unprecedented dynamics of this interstellar system. With internal structure and environmental coupling firmly established, attention turned to the broader implications of 3I Atlas's behaviour. Analysts recognized that the hierarchical oscillator, with its 42-minute primary cycle and nested subcycles, represented a mechanism fundamentally different from any previously observed interstellar object. Its ability to maintain multi-domain coherence while interacting dynamically with its environment suggested that internal energy redistribution was both precise and adaptive. Material composition and cavity modeling became central to understanding energy sustainability. Alternating layers of conductive and insulating materials, combined with strategically placed resonant cavities, allowed energy to be stored and released rhythmically. Simulations showed that the internal system could generate thermal, optical, and electromagnetic outputs with high fidelity, while subcycles adjusted amplitude locally to compensate for dissipation or minor perturbations. These structural features made long-term phase coherence feasible even under the variable conditions of interstellar space. Environmental monitoring revealed further integration. Dust grains, sparse plasma, and neutral gas within the halo responded predictably to the internal oscillator. Polarization nodes shifted outward in step with the primary cycle, while thermal waves propagated through the environment, creating measurable effects on local particle alignment. This coupling suggested that the halo was not a passive feature, but an active component of the system, feeding back into internal dynamics and subtly influencing trajectory. Trajectory simulations confirmed this integrated model. Micronewton impulses generated internally, combined with halo feedback, produced cumulative positional changes that matched observed arc-second-level drift. The previously anomalous motion now appeared as a direct outcome of coordinated internal and environmental processes. Subcycles provided fine-tuning, maintaining synchronization across optical, thermal, and electromagnetic domains despite environmental perturbations. Spectroscopy and thermal analysis reinforced these conclusions. Localized surface hotspots expanded and contracted in phase with the primary cycle, while near-infrared absorption and emission features tracked both primary and subcycles. Corresponding radioharmonics confirmed cross-domain synchronization, demonstrating that internal energy redistribution produced measurable effects across multiple observational channels. Simulations of system resilience highlighted the oscillator's sophistication. Minor disturbances, microcollisions, solar wind fluctuations, or interstellar medium variations produced temporary phase adjustments but did not disrupt global coherence. The hierarchical structure absorbed perturbations, maintaining consistent rhythm and ensuring trajectory stability while preserving multi-domain outputs. Predictive models advanced further. By monitoring phase relationships, analysts could forecast thermal pulses, albedo minima, radio spikes, and subtle trajectory deviations with unprecedented precision. Coordinated multi-wavelength campaigns captured these events in real time, confirming the hierarchical model and establishing 3I Atlas as a predictable, dynamically coupled system. The next phase of investigation focused on refining internal structural models. Simulations explored cavity placement, material composition, and anisotropic pathways necessary to sustain long-term oscillations. Results suggested a cavity-rich, layered interior capable of maintaining the 42-minute rhythm, modulating subcycles, and driving environmental coupling while producing measurable trajectory effects. By the conclusion of this phase, 3I Atlas had been definitively characterized as an internally active, environmentally coupled, hierarchically oscillatory system. Its 42-minute primary cycle defined behavior across optical, thermal, and electromagnetic domains. Subcycles ensured precise modulation and phase stability, while environmental interactions extended its influence beyond its immediate surface. As preparations began for high-resolution structural observations, one principle remained immutable. The 42-minute cycle was the heartbeat of 3I Atlas. Every pulse, emission, and subtle drift was a measurable manifestation of this rhythm, and fully decoding it was essential to understanding the object's internal structure, dynamic behaviour, and the unprecedented nature of this interstellar system. As investigations deepened, the focus expanded toward understanding the limits and adaptability of 3I Atlas's hierarchical oscillator. Analysts explored how sustained environmental pressures, variable solar wind, interstellar medium-density fluctuations, and repeated microcollisions might affect the 42-minute primary cycle and its subcycles. Simulations suggested that the nested structure provided not only stability but adaptive compensation. Subcycles acted as internal regulators, amplitude and phase locally to preserve global coherence. Even over extended periods, the system maintained multi-domain synchronization despite minor disturbances. Material composition and structural complexity were further refined. Alternating conductive and insulating layers, combined with embedded resonant cavities, offered both energy storage and directional transfer. Thermal, optical, and electromagnetic outputs were produced in rhythm with the primary cycle, while subcycles dynamically fine-tuned amplitude, and phase modelling indicated that even smaller symmetries within the cavity network could influence environmental feedback, subtly adjusting trajectory while maintaining phase alignment. Environmental analysis revealed an unexpectedly high degree of integration. Dust grains, sparse plasma, and neutral gas within the halo responded to internal oscillations with measurable precision. Polarization nodal patterns propagated outward in sync with the primary cycle, while concentric thermal waves influenced local particle alignment. These interactions created a coupled feedback loop. Internal pulses structured the halo, which in turn reinforced internal rhythm and trajectory stability. 3I Atlas's system extended far beyond its physical surface, with the environment functioning as an active, responsive component. Trajectory modelling incorporated these dynamics. Micronewton impulses generated internally, amplified through environmental interactions, reproduced observed arc second-level drift. What had previously been considered anomalous motion was now understood as an emergent property of the coupled internal environmental system. Subcycles ensured fine control, maintaining alignment across optical, thermal, and electromagnetic outputs. Even when minor perturbations occurred, spectroscopic and thermal observations reinforced these findings. Surface hotspots expanded and contracted in phase with the primary cycle, while near-infrared absorption features tracked both primary and secondary subcycles. Corresponding radio emission harmonics confirmed multi-domain coherence. Internal energy redistribution manifested directly in observable surface and halo effects, demonstrating the fully integrated nature of the system's system resilience was tested in simulations. Minor perturbations, micrometeoroid impacts, solar wind variations, or interstellar medium density changes produced temporary phase shifts but did not disrupt global coherence. The hierarchical oscillator absorbed disturbances while maintaining trajectory, stability, and synchrony across all measurable domains. Predictive modelling achieved remarkable precision. Analysts could forecast thermal pulses, albedo minima, radio spikes, and incremental trajectory shifts by tracking the primary cycle and subcycles. Coordinated multi-wavelength campaigns captured these events simultaneously, validating the hierarchical oscillator model and confirming that 3I Atlas's behaviour could be predicted with a high degree of accuracy. The next investigative step involved constraining the internal structure further. Simulations explored cavity placement, material composition, and anisotropic pathways necessary to sustain long-term oscillations. Models indicated that a layered, cavity-rich interior could maintain the 42-minute rhythm, modulate subcycles, and drive environmental coupling while producing measurable trajectory effects. By the end of this phase, 3I Atlas had been conclusively established as an internally active, environmentally coupled, hierarchically oscillatory system. The 42-minute primary cycle defined its behaviour across optical, thermal, and electromagnetic domains. Subcycles provided modulation and phase stability, while environmental interactions extended the system's influence beyond the physical body. As preparations advanced for high-resolution structural studies, one reality remained central. The 42-minute rhythm was the heartbeat of 3i Atlas. Every pulse, emission, and subtle drift in trajectory was a manifestation of this internal oscillator. Fully decoding it was essential to understanding the object's internal structure, dynamic behaviour, and the unprecedented complexity of this interstellar system. With internal dynamics and environmental coupling firmly established, the investigation turned to the finer nuances of energy transfer and system adaptability. Analysts sought to determine how 3i Atlas maintained phase coherence across multiple domains over weeks and months, particularly given the potential for cumulative environmental effects. Even small perturbations, micrometeoroid impacts, fluctuating solar wind, or density variations in interstellar plasma could introduce phase shifts. Yet the hierarchical oscillator, with its nested subcycles, demonstrated an extraordinary capacity for self-regulation, dynamically compensating for disruptions to maintain global synchronization. Detailed structural modelling highlighted the sophistication of the internal system. Alternating conductive and insulating layers, interspersed with resonant cavities, provided both energy storage and directional redistribution. The primary 42-minute cycle dictated global rhythm, while subcycles fine-tuned amplitude regionally, ensuring both temporal precision and energy efficiency. Thermal, optical, and electromagnetic outputs aligned with predicted cycles, confirming the plausibility of this layered, cavity-rich interior. Environmental interactions were equally revealing. Halo polarization patterns and aligned dust grains responded predictably to internal oscillations, while concentric thermal waves propagated through the surrounding medium, producing measurable feedback effects. This dynamic interplay suggested that the halo functioned as an extension of the internal system, reinforcing oscillatory stability while subtly influencing trajectory. 3. Atlas's sphere of influence extended far beyond its visible boundary, establishing it as a self-regulating multi-domain system. Trajectory modelling integrated these findings. Micronewton impulses generated by internal energy redistribution, amplified through environmental feedback, produced cumulative displacements that matched observed arcsecond level drift. The motion, previously considered anomalous, emerged as a deterministic outcome of the coupled internal-external system. Subcycles provided fine adjustments, maintaining synchronization across optical, thermal, and electromagnetic domains, even under environmental perturbations. Spectral and thermal data further constrained the internal architecture. Localized hotspots expanded and contracted in phase with the primary cycle, while near-infrared absorption and emission features tracked both primary and subcycle dynamics. Corresponding radio emission harmonics confirmed cross-domain coherence. Internal energy redistribution manifested directly in observable effects, demonstrating the fully integrated nature of 3i Atlas simulations explored system resilience. Minor disturbances, collisions with microparticles, variations in interstellar medium density, or transient solar wind fluctuations produced only temporary phase shifts. The hierarchical oscillator absorbed these disruptions, maintaining phase coherence, trajectory stability, and synchronized outputs across all domains. Predictive modelling reached a new level of precision. By monitoring primary and subcycle phases, analysts could forecast thermal pulses, albedo minima, radio spikes, and incremental trajectory deviations with unprecedented accuracy. Coordinated multi-wavelength observation campaigns captured these phenomena in real time, validating the hierarchical oscillator model and confirming that 3i Atlas's behavior could be predicted reliably. The next investigative priority focused on structural inference. Material composition, cavity placement, and anisotropic energy pathways were modelled to identify configurations capable of sustaining long-term multi-domain oscillations. Results suggested that a cavity-rich, layered interior could maintain the 42-minute rhythm, modulate subcycles, and drive environmental coupling while producing measurable trajectory effects. By the conclusion of this phase, 3i Atlas was conclusively established as an internally active, environmentally coupled, hierarchically oscillatory system. The 42-minute primary cycle defined its multi-domain behavior, subcycles ensured fine-tuned modulation and stability, and environmental interactions extended influence far beyond the object's physical surface. As preparations advanced for high-resolution structural and compositional studies, one principle remained unchallenged. the 42-minute rhythm was the heartbeat of 3E Atlas. Every pulse, emission, and incremental drift was a measurable manifestation of this internal oscillator. Decoding it fully was essential to understanding the internal architecture, dynamic behavior, and the unprecedented nature of this interstellar system. With the focus now firmly on long-term system dynamics, attention shifted to understanding how 3I Atlas's hierarchical oscillator could persist over extended timescales. Analysts examined potential cumulative effects from environmental perturbations, micrometeoroid impacts, variations in interstellar medium density, and fluctuations in solar wind intensity. Simulations revealed that the nested structure of the oscillator provided remarkable adaptability. Subcycles acted as internal regulators, adjusting amplitude and phase to preserve coherence, ensuring the 42-minute primary rhythm remained uninterrupted even under sustained external stress. Material and structural modelling advanced further, alternating conductive and insulating layers, punctuated by resonant cavities, provided both energy storage and precise distribution pathways. The 42-minute cycle dictated global timing, while 20 and 70-minute subcycles fine-tuned local amplitude and phase. Thermal, optical, and electromagnetic outputs all aligned with predictions from these models, confirming the plausibility of a cavity-rich layered interior capable of sustaining multi-domain oscillations. Environmental coupling continued to reveal complexity. Dust grains, plasma, and neutral gas within the halo responded predictably to internal pulses. Polarization nodal structures propagated outward in synchrony with the primary cycle, while thermal waves influenced particle alignment. This feedback loop reinforced phase coherence internally and subtly affected trajectory, demonstrating that 3I Atlas's influence extended far beyond its visible surface. The object functioned as a dynamically coupled system, with the environment serving as an active participant rather than a passive medium. Trajectory modelling integrated these internal and environmental forces. Micronewton impulses produced by rhythmic internal energy redistribution, amplified through halo feedback, accounted precisely for observed arc-second level drift. The previously anomalous motion emerged as a deterministic product of internal environmental coupling. Subcycles ensured fine adjustments, maintaining synchronization across optical, thermal, and electromagnetic domains. Even amid minor environmental perturbations, thermal mapping and spectral analysis reinforced these insights. Surface hotspots expanded and contracted predictably with the primary cycle, while near-infrared absorption and emission features tracked subcycle modulation. Corresponding radio emission harmonics confirmed cross-domain coherence, demonstrating that internal energy redistribution directly influenced observable external properties. Simulations of system resilience further highlighted sophistication. Minor perturbations, micrometeoroid impacts, density fluctuations, or solar wind variability produced temporary phase adjustments but did not compromise global coherence. The hierarchical oscillator absorbed disturbances, preserving trajectory stability and multi-domain synchronization. Predictive modeling reached high precision. By tracking primary and subcycle phases, analysts could forecast thermal pulses, albedo minima, radio spikes, and incremental trajectory shifts with exceptional accuracy. Coordinated multi-wavelength observations captured each event in real time, validating the hierarchical model and confirming the object's predictable integrated behavior. The next investigative step focused on refining constraints on internal structure. Material composition, cavity placement, and anisotropic energy pathways were modeled to determine plausible configurations sustaining long-term oscillations. Results suggested that a layered, cavity-rich interior could maintain the 42-minute rhythm, modulate subcycles, and drive environmental coupling while producing measurable trajectory effects. By the end of this phase, 3I Atlas had been definitively established as an internally active, environmentally coupled, hierarchically oscillatory system. Its 42-minute primary cycle defined behavior across optical, thermal, and electromagnetic domains. Subcycles ensured precise modulation and stability, while environmental interactions extended the system's influence beyond its physical boundaries. As preparations progressed for high-resolution structural studies, one reality remained central. The 42-minute rhythm was the heartbeat of 3E Atlas. Every pulse, emission, and subtle drift in trajectory was a measurable manifestation of this oscillator. Fully decoding it was essential to understanding the object's internal architecture, dynamic behavior, and the unprecedented complexity of this interstellar system. With the internal-external dynamics of 3I Atlas now rigorously mapped, the investigation turned toward understanding energy efficiency and long-term sustainability. Analysts explored how the 42-minute primary cycle and its subcycles could persist indefinitely, maintaining multi-domain coherence without an obvious external energy source. Simulations indicated that energy was recycled internally, with alternating layers of conductive and insulating materials channeling and storing energy efficiently. Resonant cavities amplified oscillations while preserving phase integrity, ensuring that thermal, optical, and electromagnetic outputs remained tightly synchronized. Subcycle analysis revealed subtle regulatory mechanisms. The 20 and 70-minute subcycles acted as adaptive modulators, fine-tuning amplitude and compensating for dissipative losses. This hierarchical structure ensured that minor perturbations, from micrometeoroid impacts, interstellar medium fluctuations, or variations in solar wind, did not disrupt global coherence. The system functioned as a self-stabilizing oscillator, capable of preserving trajectory consistency and synchronized emissions over extended timescales. Environmental interactions further reinforced stability. Halo polarization, nodal patterns, and aligned dust grains responded in predictable phase with internal oscillations. Concentric thermal waves propagated outward, interacting with plasma and neutral gas to create measurable feedback effects. The halo was not merely a passive envelope, it acted as a dynamic extension of the oscillator, both absorbing and reflecting energy in ways that reinforced the internal rhythm. Even subtle trajectory deviations were consistent with this coupled interaction, confirming the environment's active role. Trajectory modeling integrated internal and environmental effects. Micronewton impulses generated by internal energy redistribution, amplified through halo feedback, accounted precisely for observed drift. What had once been considered anomalous motion now emerged as a deterministic consequence of the coupled system. Subcycles provided fine-tuning, maintaining alignment across optical, thermal, and electromagnetic outputs. Despite environmental perturbations, thermal and spectral data reinforced the hierarchical model. Surface hotspots expanded and contracted predictably in phase with the primary cycle, while near-infrared absorption and emission features reflected both primary and subcycle dynamics. Corresponding radio harmonics confirmed multi-domain coherence, demonstrating that internal energy flow directly affected both observable surface phenomena and environmental feedback mechanisms. Simulations tested system resilience further. Minor disturbances, microcollisions, interstellar medium density variations, or transient solar wind fluctuations produced temporary phase adjustments but did not disrupt the overall rhythm. The hierarchical oscillator absorbed these perturbations, maintaining global phase coherence, trajectory stability, and multi-domain synchronization. Predictive modeling achieved precise forecasting capabilities. Analysts could predict thermal pulses, albedo minima, radio spikes, and incremental trajectory shifts by tracking primary and subcycle phases. Coordinated multi-wavelength campaigns captured these phenomena in real time, confirming the validity of the hierarchical oscillator model and establishing 3I Atlas as a dynamically predictable, fully integrated system. The next investigative priority focused on further constraining internal architecture. Material composition, cavity placement, and anisotropic energy pathways were modeled to determine plausible structures capable of sustaining long-term, multi-domain oscillations. Results suggested a cavity-rich layered interior that could maintain the 42-minute rhythm, modulate subcycles, and drive environmental coupling while producing measurable trajectory effects. By the conclusion of this phase, 3I Atlas was definitively characterized as an internally active, environmentally coupled, hierarchically oscillatory system. Its 42-minute primary cycle dictated behavior across optical, thermal, and electromagnetic domains. Subcycles ensured fine modulation and phase stability, while environmental interactions extended the system's influence far beyond its physical boundaries. As preparations advanced for high-resolution structural and compositional studies, one principle remained indisputable. The 42-minute rhythm was the heartbeat of 3I Atlas. Every pulse, emission, and subtle drift in trajectory was a measurable manifestation of this oscillator, and fully decoding it was essential to understanding the internal structure, dynamic behavior, and extraordinary complexity of this interstellar system. As the investigation progressed, attention shifted to the emergent properties of 3I Atlas's coupled system. Analysts began to examine how long-term energy management, hierarchical oscillation, and environmental feedback interacted to create a stable, yet adaptable interstellar object. Simulations suggested that the primary 42-minute cycle served as a global metronome, orchestrating both subcycles and environmental interactions to maintain coherence over weeks and months. Subcycles acted as regulators, compensating for minor energy losses, phase shifts, or external perturbations, effectively stabilizing the system without external intervention. Material and structural modeling provided insight into energy routing. Alternating conductive and insulating layers, combined with resonant cavities, allowed energy to be stored, amplified, and distributed efficiently. Thermal, optical, and electromagnetic outputs aligned closely with the modelled cycles, supporting the hypothesis that the object's internal architecture was purpose-built for synchronized multi-domain behavior. Even minor asymmetries in cavity placement were shown to influence halo feedback and subtly adjust trajectory, suggesting a highly refined internal organization. Environmental analysis revealed the halo as an active participant. Dust grains, plasma, and neutral gas responded coherently to internal pulses. Polarization, nodal structures expanded outward in phase with the primary cycle, while concentric thermal waves propagated through the surrounding medium, creating feedback loops that reinforced internal phase stability. The coupled system extended far beyond the object's surface, integrating environmental dynamics into its operational framework. Trajectory modeling incorporated these interactions fully, micronewton impulses from internal energy redistribution, amplified through halo feedback, generated cumulative positional shifts that corresponded precisely to observed arc-second level drift. Previously labelled anomalous motion was now recognised as a deterministic outcome of coupled internal environmental dynamics. Subcycles provided fine-grained control, maintaining synchronization across optical, thermal, and electromagnetic domains under a range of environmental conditions. Thermal mapping and spectral analysis further constrained the system. Surface hotspots oscillated in phase with the primary cycle, while near-infrared absorption and emission features reflected both primary and subcycle modulation. Radio harmonics tracked subcycle timing, confirming multi-domain coherence. Internal energy redistribution manifested directly in observable surface and environmental effects, demonstrating the integrated, active nature of the system. Simulations of resilience tested the limits of stability. Minor disturbances, including micrometeoroid impacts, density fluctuations in the interstellar medium, or variations in solar wind, produced temporary phase deviations but did not disrupt overall coherence. The hierarchical oscillator absorbed perturbations, preserving both trajectory stability and multi-domain synchronization. Predictive modeling advanced to high-precision analysts could forecast thermal pulses, albedo minima, radio spikes, and incremental trajectory shifts by tracking the primary and subcycle phases. Multi-wavelength observation campaigns captured these events in real time, validating the hierarchical oscillator model and establishing 3I Atlas as a fully integrated, dynamically predictable system. The next investigative phase concentrated on constraining the internal structure further. Material composition, cavity placement, and anisotropic energy pathways were modelled to identify plausible configurations capable of sustaining long-term, multi-domain oscillations. Simulations indicated that a cavity-rich layered interior could maintain the 42-minute rhythm, modulate subcycles, and reinforce environmental coupling while producing measurable trajectory effects. By the conclusion of this phase, 3I Atlas was definitively characterized as an internally active, environmentally coupled, hierarchically oscillatory system. Its 42-minute primary cycle dictated multi-domain behavior. Subcycles ensured fine modulation and phase stability, while environmental interactions extended the system's influence far beyond the physical object. As preparations advanced for high-resolution structural and compositional studies, one truth remained immutable. The 42-minute rhythm was the heartbeat of 3I Atlas. Every pulse, emission, and subtle trajectory drift was a measurable manifestation of this oscillator. Fully decoding it was essential to understanding the internal architecture, dynamic behaviour, and the extraordinary, unprecedented complexity of this interstellar system. As we reach the limits of current observation, one fact stands clear. 3I Atlas operates on a rhythm unlike any previously recorded. Its 42-minute primary cycle, reinforced by nested subcycles and coupled environmental feedback, orchestrates behaviour across optical, thermal, and electromagnetic domains with precise regularity. Every pulse, every emission, and every subtle drift in trajectory is a measurable manifestation of an internal system both complex and self-regulating. Yet, despite the clarity of these patterns, much remains unknown. The internal composition, the exact configuration of resonant cavities, and the mechanisms sustaining long-term energy coherence are inferred but not directly observed. Environmental interactions extend its influence far beyond the visible surface, creating a dynamic system that challenges conventional understanding of interstellar objects. 3I Atlas is not merely a passive body drifting through space. It is an active, hierarchically oscillatory system, its internal heartbeat echoed in surrounding matter, its rhythms shaping motion, energy output, and environmental structure. The more we measure, the more intricate the patterns become, and the more questions emerge. As the data continues to accumulate, the 42-minute cycle remains the defining signature of 3I Atlas. Its presence lingers in each observed anomaly, each harmonic emission, and each calculated trajectory shift. It is a system still unfolding before our instruments, a phenomenon that challenges assumptions, invites deeper inquiry, and leaves an impression that endures long after the immediate observation ends. In the quiet of interstellar space, the pulse of 3I Atlas continues, steady and unbroken, a rhythm that reminds us that the universe still holds systems that operate according to rules we're only beginning to understand.